Before working on this section, I suggest you definitely go through the polynomials as well as logarithms videos. You can look at the full logarithm section when you first come across them at the end of this topic, but I'd say definitely go through the polynomials section because I'll make explanations assuming you're already familiar with the polynomials and how to solve them. For this topic, first we'll define a function and introduce some of the related terminology. Then we'll look at inverse functions. And for the remainder of the video, we'll cover different types of functions. These being linear functions, quadratic functions, and exponential functions. And it's during the exponential functions part that we'll come across logarithms. Let's begin. So let's say you have a set A. A set essentially just being a bunch of numbers, say 1, 2, 3, 4, 5. A more structured way to write it is, and here comes the first definition. A relation is defined as a rule which links each element of set A with at least one element in set B. In simple words, it basically just means an equation. So you could, for example, have B equals to 2A, which would lead to B values of. So in this case, the rule that links each element of A, meaning each number in A, with at least one element in B, would be B equals to 2A. Each element does link with one number in B, so it matches the definition. In this case, each element in A links with exactly one element in B, so it's called a one-to-one relation. But there's two other possibilities. Let's say you had the relation y equals to x squared. You wanted to get y for x values of -2 to +2. You would get these values for y in this setup. It's a little messier in this case, and besides that, the main different thing is that now various elements in x link to single elements in y. So this is a many-to-one relation. Then there's the final possibility. Let's say the relation y equals to square root of x, and you want to get y for x values of 0, 1, and 4. You would get another messy looking diagram, but this time single values of x linked to numerous y values. So it's a one-to-many relation. Then we finally come to the definition of a function. A function is a rule which uniquely links elements of one set A with elements of another set B, with each element in A mapping to only one element in set B. It's basically the same as a relation, but it's restricted to one-to-one relations and many-to-one relations. Whereas one-to-many relations, such as the y equals to root x relation we had from earlier, these cannot be considered as functions. So only equations that are one-to-one or many-to-one can be considered functions. Now I'll just clarify on some more terminology and what it means. First we have f of x. The f stands for function, and the f followed by the x in brackets means a function of x. Then this will be equals to some equation in terms of x. Examples of such an equation would be some of the ones we already looked at, such as x squared, which would be a many-to-one function. Or say, even the very first example we looked at, but say we had it as x over here instead of a. In that case, we would have fx equals to 2x, which would be a one-to-one function. But of course, we wouldn't be able to write square root of x on this side because it is a one-to-many relation, so it doesn't qualify as a function. The next thing to note is that the function doesn't have to only be indicated using the letter f. It can be anything. Like if you're talking about two or more different functions, you could represent the other functions using things like g of x and h of x, or even w of x if you so please. But for your tests and exams and stuff, you most likely only see g of x and h of x. Another thing is that the term in the brackets, which has just been x so far, could be anything. It just needs to be whatever the independent variable of the equation is. So if you had a equals to b squared, since a would be a function of b, you could replace a with f of b, and you'd have f of b equals to b squared. So the term in the brackets just needs to be whatever shows up on the right side here. Next thing to note is that the notation fx is just a convention for indicating that some variable is a function of another. So if we had the equation y equals to x squared, you could write fx equals to x squared, and in this case fx would just represent the dependent variable y and can be considered equal to y. So fx and y can often be used interchangeably. Then lastly, related to the fx notation is, say for example you're told that fx equals to 2x plus 3, and you need to determine when fx equals to 7. You just treat fx like if it was a variable whose value is 7, then equate this equation to it and solve for x, which would finally give you the x value as 2. But then, if the question said you need to solve for f of negative 4, you would find the value of fx when x equals to 4, since x is what's usually in the brackets. Then just substitute that in and you get fx as negative 5. So when you're told that the function itself is equal to some value, you equate the whole equation to the value, such as over here. But if you're told to find the value of the function with some number in the brackets, you assume whatever variable is usually written in the brackets has that value. Then you just substitute it in. And lastly, just a reminder of the meanings of domain and range, which you've probably seen before, but it's worth refreshing as it will be used a lot in this video. The domain of a function fx is a set of values for which the function is defined. So the values that you're allowed to input to the function, meaning the x values. A simple example to demonstrate the meaning of the domain is the function 1 over x. What values of x are we allowed to have, or rather, for what values of x is the function defined? Well, basically anything except for 0. So the domain is x can be any real number except for 0. The systematic way to write this is, what this means is that x is an element, that's why it sort of looks like an E. So x is an element of the set of real numbers. Basically just saying that x can be any real number. And then what comes after the semicolon describes which numbers are exceptions to this, which in this case would be 0. So you just state that x isn't equal to 0. Next, there's the range. And the range of a function is the set of all values that f can have. So for the same function 1 over x, for example, it's easier to understand if we look at its graph. So domain restriction can clearly be seen where, as you look at the graph while going along the x-axis, the graph tends to infinity at 0, meaning there's a vertical asymptote at 0, and then it returns to normal behavior. And for the range, we look at the y-axis and see what happens to the graph as you move along the y-axis. So we can see it's going normally, but then there's a horizontal asymptote as y reaches a value of 0, meaning at the x-axis. Then it returns to a normal value after 0. Therefore, it seems like the function can have any real value except for 0. So that would be the range. If you're still a little bit confused about domain and range, it'll become clearer when you look at examples of the different types of functions. For the final part of the definition and terminology part of the video, it's not so much related to any definitions, but it's more so a useful method of how to determine whether a given relation qualifies as a function. And that too a method without drawing all these funny diagrams from earlier with all these arrows and stuff. And it's called the vertical line test. If you have the graph of a certain equation, the vertical line test is a nice and quick method to determine whether a relation is a function. What it says is that if it's possible to draw a single vertical line that passes across the graph more than once, then it's not a function. Let's try out some equations. This is the graph for y equals to x squared. So here's a vertical line to test it out. So what happens when it's passed along the graph? As I pass it across the graph, it only ever intersected with the graph at a single point, and therefore it qualifies as a function. And it would be completely fair to write it as fx equals to x squared. How about the equation of a circle? The equation of a circle with its center at coordinates a, b is x minus a squared plus y minus b squared equals to r squared, where r is the radius of the circle. You don't need to know this equation. Just take from this example what happens when you apply the vertical line test to this case. To keep it simple, let's just take the center as the origin, meaning a and b would be 0. And let's just randomly take the radius as 3. Then just substitute this all into this equation and you end up with x squared plus y squared equals to 9. And the graph for this is, so what happens when this vertical line is passed across it? So we can already see that it intersects with the graph at 2 points. And that is enough for it to fail the vertical line test. So even if at just a single point of the graph, the line crosses the graph more than once, that's enough to say that the relation isn't a function. But for this case, you can see that this happens at pretty much all x values across the graph. Therefore, this doesn't qualify as a function. And with that, we've covered most of the basic terminology and definitions related to functions. If the vertical line test is still a bit iffy in your mind, don't worry. It will be covered in various other examples in the leftover parts of the topic, so you'll get more chances to see it in action. Moving on, the next part is inverse functions. An inverse function is a function that does the reverse of a certain given function. This is best understood through a simple example. Say we have the function 3x plus 2. The inverse function would be f inverse x equals to x minus 2 over 3. To demonstrate this whole reversing of the original function, let's focus on what happens to any value that you input to the original function. The original function is 3x plus 2. So the input to this would be an x value. The sequence of things that happen to an x value in this function is, first it's multiplied by 3, then 2 is added to it. Then we look at what happens to any value we input to the inverse function. The first thing that happens to the x value is that 2 is subtracted from it. It is definitely divided by 3, but that only happens after 2 is first subtracted from it. So first thing you do is subtract 2 from it, and after that it's divided by 3. Now everything is set up to show this reversal. So for the function 3x plus 2, you first multiply x by 3, then you add 2 to it. And for the inverse, you do the opposite of these in the reverse order. For the function, you multiply by 3 first, but for the inverse, you divide by 3 second. And for the function, you added 2 second, but for the inverse, you subtracted 2 first. I think that example demonstrates the basic idea pretty well. So not every function has an inverse function. Only one-to-one functions have inverses. That means if you have a many-to-one function, while it does qualify as a function, it won't have an inverse function. One of those set diagrams from the beginning will be pretty useful to explain why that's the case. Earlier on, we looked at the equation y equals to x squared and established that it was a many-to-one relation. So as a function, it would be fx equals to x squared, and it would be a many-to-one function. So the inverse, we would be looking at it from the opposite direction. So let's reverse the arrows. Okay, you can see something is happening, but it's a little confusing seeing it in this opposite direction. So let's mirror it. Okay, now it's easier to see what's happening. The function in reverse has single values with links to more than one number, such as 1 with these various links, and 4 with these 2 links. And as per the definition of a function, each number in the first set can only link with one number in the second set. But this reverse function, on the other hand, is one to many, but it wouldn't be a function. Then the only other function left is the one-to-one function, and an example of such a function is the one we saw at the very beginning, the whole b equals to 2a1, which had the diagram. And let's just adapt it to being in terms of x and y, so it's a bit more familiar. Since y is a function of x, we can write this as fx equals to 2x. And with the inverse, we're looking at it from the reverse direction, so let's reverse the arrows. Then just mirror it, and this time when looking at the function in reverse, every number only links to one number in the other set. So even the inverse has a one-to-one relationship and therefore qualifies as a function. So that should demonstrate why only one-to-one functions are invertible. Those are the basic ideas behind what an inverse function actually is. So the next thing to ask is, how do we determine an inverse function? Before I explain this, it's an important point to make clear right now, which is the inverse of a function isn't the same as the reciprocal. This is quite easy to mix up because they're both written in a very similar way. In case you don't know, the reciprocal of something means 1 divided by it, and it's represented with an exponent of -1. This whole -1 superscript is used for both, but for the reciprocal, it comes after the whole fx term has been enclosed in brackets. And it means what it usually does. But for the inverse, the -1 is after the f and before the x in brackets, and doesn't represent an exponent, but is rather just a notation for indicating the inverse of a function. The difference can be seen using the 3x plus 2 function we've already been looking at. The inverse function would be x minus 2 over 3, and the reciprocal would be 1 over 3x plus 2. Both of these are clearly very different. That was very important to first clear up, but now moving on to how you actually determine the inverse. The process consists of 3 steps, the first of which is swapping x and y in the equation. Now what this means is that you turn every x in the equation to a y, and every y in the equation to an x. If we apply this to the 3x plus 2 equation we've been looking at, you have it in function notation, so you first change the fx to a y, so that you actually have a y to turn into an x, and you swap x and y to get x equals to 3y plus 2. Next step is rearranging what you have to make y the subject. When you do this, you will get y equals to x minus 2 over 3. Then the final step is just writing this in function notation. You finally get the inverse function as f inverse x equals to x minus 2 over 3. And that's it. We'll practice it a bunch of times with the different types of functions we'll look at in the next few sections. The last thing under inverse functions is the visual representation of it. When you plot the graph of a function and its inverse, the two graphs will be reflections of each other about the line y equals to x. For example, with the 3x plus 2 function, whose inverse was x minus 2 over 3, you get the following graph, where the function 3x plus 2 is up here in blue, and its inverse x minus 2 over 3 is down here in orange. It's pretty easy to see that they're reflections of each other about the line y equals to x. If you want a more complicated example, we can look at the function fx equals to x cubed, whose inverse would be the cube root of x. The graph looks like this, where x cubed is here in blue and starts at the top, then it goes under y is equal to x, then it goes above it again, and finally ends up under it. Then the inverse function is the opposite. It starts below the y equals to x line, then it goes above, it comes below, and finally ends up above it. And again you can see that they are reflections of each other about the line y equals to x. And with that, we've set a pretty solid foundation for functions and inverse functions. Now to see how they look for different types of functions, starting with linear functions. The general formula of a linear function is y equals to ax plus q, which is basically the same as the usual formula for a line mx plus c, but it's just a special notation for when you're talking about a linear function. In function notation, this would be fx equals to ax plus q. But if you remember, I said at the very beginning of the video that it doesn't have to be fx. Any letter can be used, so even something like nx would be fine. Let's look at an example of a linear function. So we have a linear function g of x equals to 4 minus 2,5x, and we need to determine the inverse of this function and sketch both the function and the inverse. To find the inverse, you just follow the same 3 steps I mentioned in the previous section. First, you have to swap x and y in the equation, so replace every x with the y and vice versa. The equation is in function notation, so let's change it to a simple x and y, giving us y equals to 4 minus 2 comma 5x. Then you swap x and y, giving you x equals to 4 minus 2 comma 5y. Next is you need to make y the subject, which gives us y equals to 4 minus x over 2 comma 5. Lastly, you just put it in function notation and you get g inverse as being equal to 4 minus x over 2 comma 5. So we have the inverse function now. We just need to sketch their graphs. Earlier, when I was introducing all the main concepts related to functions, I didn't spend too much time on the details related to sketching the graphs, mainly because from previous grades, you should have sketched graphs many times, so I didn't want to waste time repeating things you already knew. But now that I've set a good foundation for functions, I'll start talking more about details related to the sketching, because it's definitely an important aspect of understanding functions, and you need to be able to sketch for your exam. The approach I'll take is, I'll usually show you how to calculate any important or new key information needed to plot the graph, but I'll assume you're familiar with things such as turning points, intercepts, axes of symmetry, etc. Then I'll just show you the nice final graph, assuming you'll have done all the necessary hands-on sketching by yourself. That being said, how do we sketch the function and its inverse from the question? For a linear function, all you need are the x and y intercepts. At the x-intercept, y equals to 0. Then just substitute that into the equation and solve for x, which you get as a value of 1, 6, making your y-intercept as 1, 6 and 0. And for the y-intercept, x equals to 0. And when you sub that in, you get the y-intercept coordinates as 0 and 4. Now with the x and y intercepts, we have enough info to sketch g of x. We just need to repeat the process for g inverse x. When we do that, we get x-intercept as 4 and 0 and y-intercept as 0 and 1, 6. You can now sketch both graphs, which will look something like, with gx in blue and g inverse in orange. Having the graph in sight, I'll bring up one interesting point. Looking back at the various coordinates for the different intercepts, you may have noticed they look pretty similar. For g, you have coordinates of 1, 6 and 0 and 0 and 4, whereas for g inverse you have 4 and 0 and 0 and 1, 6. So they're pretty much the exact same coordinates, except that they are reversed. Coming back to the graph, the x-intercept for g is reflected across y equals to x to give the y-intercept for g inverse. One has coordinates of 1, 6 and 0, and the other has coordinates of 0 and 1, 6. So they are the reverse of each other. And same story for the other point. The x-intercept of g inverse is reflected across the line to give the y-intercept of g. One has coordinates 4 and 0, and the other has coordinates 0 and 4. This shows a certain pattern. Don't worry about the intercepts. All it shows is that any point reflected across the line y equals to x will keep the same coordinates, but with x and y coordinates switched around. One more example. This question is asking whether the relation x minus 2y equals to 3 is a function. Whenever you're asked whether something is a function, the best method for doing this is draw the graph and do the vertical line test. We have x minus 2y is equal to 3, so I'll first make y the subject so it's in a more familiar form, giving us y equals to x minus 3 over 2. And when sketched, this gives. Then we just try the vertical line test. We can see that the line never cuts the graph at more than one point. In your case, you could do the vertical line test just using a ruler. And since this passed the test, then yes, it is a function, since a vertical line only ever cuts it at one point, meaning that there's only one y value for every x value. And related to that, every linear function has an inverse, except when the gradient is equal to 0, meaning if a in this equation is equal to 0, then this x term will cancel out, and you will just have something such as y equals to 2. And while it will count as a linear function, it won't actually have an inverse. Now moving on to quadratic functions.